All right, welcome. This is the AP Physics multiple choice solutions for conservation of energy. Here, this is the first part. I'm going to be covering questions 1 to 12, which is basically the first page. All right, so we have number 1 here. It says a mass is tied to a 1 meter string. The string is attached to a point on a horizontal frictional surface and the mass is set in a circular motion. The string will break if the tension becomes larger than 10 newtons. The maximum kinetic energy that the mass can achieve before the spring breaks is what? Okay, so a couple things here. You're dealing with force and energy here. So let's look at what the question's asking for, okay? Because some of you might be confused on what we're even asking for. First of all, it says the maximum kinetic energy. So you want a value of Ke, right? Or we just write K in class, Ke, right? You want some kinetic energy, which is 1/2 mv squared. You want that, okay? So to get this, you need mass and velocity. Do you have mass here? Do you have velocity? No, but you need it. That's the only kinetic energy equation that you have. So what can you use, right? What you have is you have a tension force, which can no longer be 10 newtons. So you can write here tension is equal to 10 newtons once it breaks, and you also have a mass is tied to a 1 meter string. So that looks like that is a value, like a distance value or a radius value. So we can write x equals to 1 meter, or you could also write radius equals to 1 meter. Not quite sure, but we know we have some distance of value. Okay. All right. So how do we go from here to here? I know that there is some mass and some acceleration in the tension force. Maybe I could work with that. So let's break that down. Maybe we could break this down somehow. I know that my tension equals to mass times acceleration, and that will be equal to 10 newtons. Okay. My issue is, do I have mass? Not quite sure. Do I have acceleration? Ooh, it seems like I do because the mass is set in a circular motion. Circular motion tells us something very interesting. The mass is in a circle, and we know what's being pointed inwards is centripetal acceleration. And we know in our formula sheet, if you look at it, that centripetal acceleration is equal to velocity squared over r. Why did I decide to do this? This had v in it, and remember, I have to have a v in my final equation, so that's why it's useful. Also, something else that should be interesting is an r popped out. We also have an r. Seems like we're working in the right path. So let's make that substitution. Let's make that substitution for a, becomes v squared over r is equal to 10. Wow, this seems really interesting. We needed a what? mv squared, and we almost have an mv squared. Okay, what we can do is a little bit more algebra. We know that mv squared is equal to 10r if we multiply by r to both sides. Perfect. Seems like we have a perfect substitution here. So let's make that substitution. Okay. K is going to be equal to 1/2. And we know that mv squared is equal to 10r. Perfect. And we multiply. This is perfect because we actually already know what our r is. Times 10. What is our r? We know that as 1 meter, so we could be times that by 1. And the final answer here, 1/2 times 10 times 1, it's just 5. And this is kinetic energy. The units for kinetic energy is joules. So that would be your correct answer, 5 joules. Number 2. Okay, a car A has a mass m and moves at a speed 2v, while a car B has a mass of 2m moving at speed v. What is the ratio of the kinetic energy of car A to that of car B? So here, let's just look at the question. We want a ratio of the kinetic energy of car A to car B. So ratio means we need a fraction. Kinetic energy, so I write K of car A. The bar here is the word to. The bottom is car B. And we want the kinetic energy, so I can make some substitutions here. We have 1 half mv squared divided by 1 half mv squared for this. Okay, a couple of things. Okay, a couple of things here. What we can do is that the first car has a mass m and moves at speed 2v. So what happens? All right. So we can make some substitutions here. 1 half m, and we know v is what? 2v squared. And the bottom is 1 half. We know that it's 2m, so we write 2m v squared. Okay? All right, so let's just bring this out a little bit more here. So again, I'm going to carry on the work. To this side, please continue the work. Like imagine like I'm going down. Okay? Then it looks like, okay, so I can cancel out a couple things here. So this looks right here, looks like it got me 1 half m. I have a 4 because 2 squared, right? Here, if you want to see it, it's 2 squared, v squared. These cancel, this becomes 4. Okay, so it becomes 4 v squared. The bottom is 1 half 2 mv squared. All right, so things that can cancel out. Looks like a 1 half cancels out, a 1 half cancels out. We have an m canceling out, we have an m canceling out, we have a v squared canceling out, we have a v squared canceling out. So we have a 4 on top and a 2 on bottom, which can be simplified into 2 over 1. So the answer is B. Okay, the ratio of the energy of the ratio of the kinetic energy is 2 to 1. Good. All right. Three. In order for an object to have useful potential energy, the object must have which one of the following? So let me give you an example of a useful potential energy and something with not useful potential energy. Okay, so this would be useful here. Useful, all right, is that if I have a ramp and I have a block, it's at rest. I hold it. If I let it go, once I let it go, when I let it go, it slides down here. Okay, I don't even have to apply it because you know what slides it down? It's the mg sine theta that is pushing it down. Okay, the sine part of gravity. Good. What about not useful? Not useful. If I have a table and I have a block right here and there's a height. I know there's a height, right? There has to be a height. Here there's also a height. Okay, there's also a height here. Okay, and the object falls. So there's a force, right? This is the force. But also please understand that there is a potential energy of gravity that is mgh here. Here there's also a potential energy of gravity of mgh. But if I let this go, the object stays at rest. Even though there is a height. Why? There's no force. There's no force interaction here. Force isn't doing anything here. It just stays at rest. The potential energy here does not do anything. Okay? So, first thing, the potential energy must have a positive value. Not quite. No, because here potential energy has nothing to do with positive signs or not. So this doesn't work. Okay? The object must have energy associated with its position. Okay, here it has energy, right? mgh. Okay, useful. Here it has potential also, mgh. It's a mass, there's gravity, and there's also height. But this is not useful. But there's still energy associated. Makes no sense. Okay. The object must, so I'm going to skip C, but let's go to D. The object must have kinetic energy. This object has no kinetic energy. I just let it go. Okay, it gains kinetic energy, but it never had kinetic energy at the start, but it's still useful, right? It's wrong. The correct answer is this. The object must be able to lose its potential energy when it released. Once I let this block go, the mgh gets converted, right? It gets converted to um, 1 half mv squared. Why? Because there's a force of mg sine theta that is causing it to go down. You see, the mg sine theta is forcing the object to go down, converting the potential into the kinetic. So the object must able to lose its potential energy. That's the key part. Lose its potential energy when released. This block on the table does not lose any potential energy once I let it go. 4. Right? A block starts at rest at a height 20 meters and slides down from a move incline. What is the block speed when it reaches the ground? Okay, we did this in class, but I'm still going to go over it. Okay, so a couple of things here. We want to set up our equation from the start. So I'm just going to start it up. The summation of energy 1 is equal to the summation of energy 2. And we know that all the parts for this is we have u of spring plus u of g 1, spring 1, plus kinetic of energy 1 is equal to u of spring final or 2 plus u of g2 plus kinetic energy of 2. Okay, first of all, things can cancel out. Is there a spring here? No, so this goes away. There's no spring. Okay, good. The object is at rest at the start. Okay, the block starts at rest, so let me underline that. The object starts at rest, so that means V initial is equal to 0. So that means K1 is also equals to 0. Okay, because there's no kinetic energy at the start. So K1 goes bye-bye. Okay, from a height in a smooth surface. And we also have one more piece of information that's very crucial. It reaches the ground. Reaches the ground means height 2 is equal to 0. So, bye-bye potential energy. So all you have left here is our traditional gravitational potential energy 1 is going to be all converted to its kinetic energy at point 2. So this is mgh 1 is equal to 1 half mv squared, and this is velocity 2. All right, so let's see. Oh, look, masses are both here. So cancel those out, cancel those out. All right, and let's solve for block speed, right? Block speed. So we are looking for V2. Okay, so let's work through some algebra. I will multiply by 2 first, so it's 2gh is equal to v squared 2 square root. So square root 2gh is equal to second velocity. Now you plug things in. 2 times 10, what's the height? 20 is v squared, which you should get, sorry, v2. v2 should be around 20. Good? That's your answer. Good. Make sure you work through the algebra. Things will cancel out. Plug in the numbers as the last step. 5. It requires a force F to stretch a spring a distance x In the process, an energy U is stored in the spring. If the spring is stretched 2x, what is the force required and the energy stored? Okay, good. Um, First of all, we want to look at F stretches the spring x distance. So here, this is referred to Hooke's law. I don't even know if that's how I spell his name. Hooke's law. K, no. Restorative force, right? The spring force is equal to negative kx. Remember, this is just distance. This just gives a distance, okay? Okay. We know that in the process, a u is stored. So traditionally, this makes a u, okay? And what is potential energy? 1/2 kx squared, okay? So if we do this, it gets us this, okay? If the spring is stretched to 2x, so let's do, and that happens, it's 2x now, okay? If it's 2x, if we multiply this by 2, force also has to go 2. Why? Because x is directly proportional to force, right? Because there's no square term here. So if I double this, this has to be doubled. So for this to balance, it has to be 2f is equal to k 2x. Good? So the force has to double because it matches here. What is the force required and the energy stored? So if this becomes 2x, right, becomes this because x is directly proportional to force. What about u? If we if we put the x as 2x, remember there's a squared term here. So watch what happens. 1/2 k, 2 squared is 4, and this is an x. To balance this, okay, to balance this, what happens here? It what? There's a 4 here, so this also has to be 4 to balance it out. Okay, because the oops, sorry. Because the 4 needs to balance out. Okay, and there's a squared here. There's a squared here. There's a 4, so we need 4 u 2f 4 2f 4u. Good. Why? Because the for potential energy of a spring, the x, right, because of the squared, the x is squared proportional to energy, to u, okay, potential energy, okay, because of the squared term. Which graph represents Hooke's law? Again, you could just memorize this. If not, okay, so what is Hooke's law? We also did this in class. We know that Hooke's law is F is equal to negative kx. Okay, but again, that negative is just for direction. Okay, so you can almost treat it as this if you would like. This is a magnitude. Magnitude. I don't even know how to spell that's magnitude. Magnitude of the spring force. Okay, real physics people would kill me right now. Okay, but I'm a real physicist, so okay. This is just short nomenclature of the idea. Okay. You could just absolute value to get the magnitude. Okay. What episode, what represents Hooke's law? We know that F is equal to Kx. Okay. Think about where it's starting. Okay. Okay. What is the term? 1 here, right? It's a power of 1. Which one has a power of 1? No, this makes no sense. This is like a power 2. This is like not even inverse, maybe. This is flat, not quite sure. But this is a constant, so there's no variable. C makes sense, but I could show it to you. Remember, what if x is equal to 1? What's the force? So I could even write you the example. So if k is the spring constant, right, we can just treat that as like 1. Okay. What is x? 1. So what is f? Just 1. Okay. What happened if we make these 2? Okay. So 1 for k, 2 here. Force is 2. So 2, 2. So look. 1, 1. 2, 2, 3, 3. Okay, this has a linear relationship. And what do we say? Hooke's law, F is equal to Kx, is reminding us of y equals mx plus b, where the spring constant is equal to the slope. So the slope here is also equal to the spring constant. Okay. Good. Let's drop this over, go back up. Let's go to 7. 7's up here. Yep. Okay. So for an object to be moving in the x direction, what condition must be met for work to be positive? Okay, a couple of things we need to understand. Work is equal to, same. There's different ways of writing it. Force, delta x, and there's a weird parallel here. The force, the force needs to be applied parallel in the direction. In other words, F is equal to F. Work is equal to force times, okay, delta x cosine theta. You might have seen that version, or you could also see work is equal to change of kinetic energy, all right, or K. Here, there's no kinetic energy. It seems like we're dealing with some thetas, so we are probably working with this version of the work equation. There's a lot of different work equations, but they represent the same thing. Okay, we need to understand that work has a direction, because again, y work is a force, is a vector. That would be the correct word. Okay, so, and there's an F here. There's a force involved here. All right, so the force and displacement vector must be in the same direction. Yeah, that works, right? If we for it to have what? Because for an object moving in the x direction, so let's just draw that x direction. What condition must be met for the work to also be positive? So anything this way is going to be positive, and we want the work to be positive. So we want work to go that way. To work to go that way, the force also has to be that way. What do I mean by force? I am talking about force net has to be that way. Force net has to be in the same direction as work. So work is technically, this F is actually F net. Okay? Delta x cosine theta. Okay. So the force and displacement vector must be in the same direction. Yep, that looks good. A component of force must have the same direction as displacement. No, can't be a component. It has to be the whole force. The angle between the force and displacement must be 0 degrees, and the angle between force and displacement must be less than 90 and less than 90 and more than negative 90. What? So wait, hold on. What? Are you saying the theta here has to be less than 90? If theta is less than 90, it's going to change this. An angle between force and displacement must have 0 degrees. So if theta equals to 0, then the F equals to F net delta x cosine of 0. Cosine of 0, note that cosine of 0 is equal to 1, so F net delta x is equal to 1. So here it becomes in the same direction. So this is correct, right? So the force of displacement must be in the same direction, and the angle between the force and displacement must be 0 degrees. That is how you get the force to be moving in the same positive direction as your force. Okay. Can I give a side note here? I'm gonna give a side note about this. Okay. So here's a block and here's force. Work is once you have this force moved a delta x. Okay, and this is what I mean parallel. So right here, the force is being applied to that distance. The distance is also to the right. Here you get your maximum work. But what happens if the force, okay, is going this way and your delta x is this way? Okay, there is a theta that is involved. So your work is equal to force net delta x cosine of something, right? This is going to be a value that is less than 1. So it's going to get smaller, okay? So this is going to make this smaller. As theta approaches 90 degrees, the work decreases to 0. So what do I mean? If your work, if your force is this direction and your delta x is this direction, and here you have a box that is 90 degrees, or theta is 90 degrees, watch what happens to the formula. Work is equal to F net delta x cosine of 90 degrees. What is 90 degrees of cosine? 0. So work is equal to 0. When theta equals to 90, the work is perpendicular to the displacement. The work becomes basically 0. So if it's right at 0 degrees, it's maximized. As it gets going up, 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 it gets smaller and smaller. Once it hits perpendicular, the work becomes 0. The area under the force displacement graph is what? Okay, so let's just take a look. Here's the graph, and it is the force. So here's force. Here is displacement, and for displacement, I'm just going to use that notation of delta x. Okay, and we can draw a line here. Right? Force is being applied steadily. So let's say, like let's say it's a horizontal block. Okay, and the force is being applied at like 10 newtons. Here we could write 10 newtons, and it's being applied over delta x is equal to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? It's always being displaced. So at 1 meter, 10 newtons of force. At 2 meters, it's still 10 newtons of force. So it should look like this. Okay, and you want the, let's see if I can fill this. Right, we want this area, right? The area under the curve. Okay, what is this area under the curve? If you really want to think about it, what is the area? What is the? It's very easily if you really think about it. What is the area here? Right? How do I find the area? This is a rectangle. What is the area of a rectangle? Length. In this case, it's what? Length times width. But you know what the length is. The length is force. What is the width? Displacement. So length was really force. What is displacement? Delta x. What's another way of writing force times delta x? The area is actually the work. Because again, it's a rectangle. Right? Just length times width. 9. The work of an applied force that is required to accelerate a car up a hill is equal to, okay, let me show you here. All right. Here we have a hill, and here the hill has a height, And right here we have a car. The accelerating doesn't mean anything. Well, it means there's a force, but here's the car. That's a pretty good car. And we want the car to go up here. Okay? And we want to look at the work. Okay? We know that work is equal to what? Force times delta x. Okay? What is the delta x in this case? Technically, we always think about delta x as what? Delta x, we always think about delta x as like um, horizontally like this, but delta x could also go up. We don't call it delta x when it's up and down. We actually call it what? Delta y. What's another word for delta y? Height. So really, force, right, times height. But what is force? We know force is really what? Mass times acceleration. Okay? But what is, when we look at this vertically, right? The force, right? Mass is the same, but what is the acceleration in the vertical? It's what? Yes, you are correct. Gravity. So the force is really mass times gravity when it's vertically. Okay? So this really breaks down to what? Oops, sorry. Force breaks down into mg. Delta x was actually h. This work, right? That is being applied, okay, vertically is just what? mgh, which is just gravitational potential energy. Okay, all right. Which of the following is true when conservative force acts? The energy of a system remains constant. That is correct, right? This is just the law of conservation of energy. This means that the sum of energy 1 is going to be equal to the sum of energy 2. Potential energy can increase or decrease. Oh, that's true. The object's path is a factor in determining change in its potential energy. Oh, this is so wrong. Okay, the path is independent. Okay, is a factor. This is so wrong. Is not a factor. Okay, why? If you look at this, look at MGH equation. All this care is about its initial spot and its final spot. So what does that mean visually? That means that this, someone that goes here and someone that does this has the same amount of energy because energy is independent of path. Okay? All they care about is initial and final. Conservative force can only increase its velocity of an object. Conservative force can only increase the velocity of an object. What? No, an object can lose. An object can lose its velocity. Okay? An object could lose its velocity from it being converted to potential energy. So let me show you why this one's wrong. Imagine a roller coaster, right? So if it starts here and it rolls down, right? It all up here it has all potential energy, right? It just has u. Here, right? Once it hits the minimum, it has all k, right? When it has all k, this is when, right? When it has all k, this is when all k, this is when velocity is at its max. Okay, when it goes back up, it loses its kinetic energy and becomes all potential. And potential, right? There's no v in there. And up here, it becomes when here up here. This is when velocity is it's min. Why? Because it's basically zero. Because there is no k at the top. Why? There was no k at the top here, so there's no k here as well. So this wouldn't make sense. And again, I'm only talking about this linearly, okay? It's weird when we're talking about rotational stuff. So if it says selects 2, C and D wouldn't make sense. This would work. Potential energy can increase or decrease. I kind of said it here. Look, it decreased, then it increased. 11. An applied F pushes a block horizontally around a rough surface with force of friction F. The resulting motion is a constant velocity over a distance d. What is the net force? Oh, is this picture for this one? Oh, cool, neat. So the result, what is the net? Oh, that's interesting. What is the net work? I don't care about these. That's useless. Okay, only left to right. Okay, so work is equal to F delta x cosine theta, but it seems like there is no cosine theta, right? Well, there is a theta, but the theta is like 0, so this goes to 1. So work is just F delta x, okay? Because you see, it's parallel. All right, cosine theta is 1. Okay. But we know that it's rough surface. The resulting motion is a constant velocity. Constant velocity means acceleration equals to 0. Again, this F really means F net. So what is F net? I'm just going to throw that into the side right here. F net in this case was what? F force applied minus force mu. But we know that this is equal to what? 0 because there is no acceleration. So force applied is equal to force of friction. So if force applied is equal to force of friction, these two both cancel out. So work is what? This becomes 0 delta x. So work becomes 0, right? Because it's constant velocity over it's constant velocity. So there is A equals to 0. So F net has to be equal to 0. So it becomes 0. So work net equals to 0. Okay. Here is a very weird thing about this question. Okay, let me just type this out because you're not going to listen to me. The net work is 0. Okay? Because the net force is 0. There is still work. Okay? There are 2 works in this system. Okay? There is a work to the right and a work to the left. Okay, the one going to the right is caused by the F, and the one that's going to the left is the work by friction. Oh my god. Okay. It's work by did it cut off? Friction. Oh my gosh. Still the work by friction. Okay. There's still force. Okay, there's still forces. There's a force F that goes to the right, and there's a force to the left. They still exist. The work still exists, but the net is 0. Okay, the net is 0. There's still work being applied, but the net is 0. Okay, mass M in the diagram is accelerated to the right. Which of the mass in the diagram? What mass? Oh, is it talking about this one? Uh, in the diagram, accelerate to the right. Which of the following is true? Work for it's this one. So let me just redraw it. So here's the mass. You have F. You have force of friction. You have normal, and you have Um, Wait, did they use W for weight or no? They call that force of gravity. Okay. All right. So, is accelerating to the right. So, accelerating to the right means the F. That's bad. I so I would say that if it's accelerating to the right, F net there, F net is a value. There's something here. There's a value here. It equals. There's a value here. Okay, and it's a positive value because it's going to the right. All right. In the diagram is accelerating to the right. Which of the following is true? Okay. So if force is going to the right, if F net is positive, so if F net is positive, work is equal to F net, right? Um, Times delta x, right? Uh, so if that exists, what needs to happen? Okay, it goes to the right, so there needs to be. This is going to the right. This also has to go to the right. So the mm, oh, they broke this up. So what they're saying here is, so here they're breaking it to its component. So do you see force is going this way? They're saying there's a work caused by the force that's also going this way. Okay? What's pushing it back is the work caused by friction. So there is a work caused by the applied force and against it is the work of friction. Because it's accelerating to the right, we know that for it to go to the right, work of force has to be greater than work of friction to move right. But for it to move left, it's the opposite because force of friction would be greater. If F equals to 0, if the work of the force is equal to the work of the friction, okay, sorry, this is move left, and this would move. This is at equilibrium. Okay. So if it's accelerate to the right, it's this one. So it would be something like this, or something like this. It wouldn't be this one. Okay. Now, what also has to happen? People don't understand, but there's actually work up. There's a work caused by the normal force, and there is work by gravity. But is it going up or down? Right? It's not. So I could even write it here. Work of normal, if work of normal is greater than the work of gravity, this means it floats up. If work normal is less than work of gravity, this means it um it mm, it digs in the ground. It keeps digging in the ground. If work normal is equal to work gravity, this means it's at equilibrium. So here it's stationary. So it wouldn't be this. It wouldn't be this. It's stationary, so it would be this. So the answer here would be C. All right. So there you go. Those are all your solutions.